lesson, we're going to be looking at the graphs of the tangent and cotangent functions. So originally, we started by looking at our sine and cosine functions, which were basically just infinite waves that bounced back and forth along the x-axis from y equals -1 up to y equals +1. We then took a look at the secant and cosecant functions, which had quite a few vertical asymptotes. And the reasons they had vertical asymptotes were simply because they were reciprocals of cosine theta and sine theta. So if they're reciprocals, there's certain times where the denominator would equal 0. We're now going to investigate the curves for tangent theta and cotangent theta and use what we know about secant and cosecant to help us with that. Recall that secant of theta is the reciprocal of cosine theta, and cosecant theta is the reciprocal of sine theta. So if there's ever a time where cosine theta is equal to 0, that's going to cause there to be an asymptote for secant. And any time where sine of theta was equal to 0, that would cause there to be an asymptote for cosecant. So if we take a look at our values here, we can see that secant has asymptotes at the locations where cosine is equal to 0. So let's think about where cosine is equal to 0 on our rotation. So keep in mind cosine is our x-coordinate. So the x-coordinate is 0 at pi/2 and at 3π/2. And there's other locations as well if we really want to get into it. We could say on any rotation, so we could have perhaps pi/2, we know that there's going to be an asymptote. And we saw there was another asymptote at 3π/2. But maybe we even look before that, and we look in the negative direction, or look at the negative rotation, and -π/2 would be one, or 5π/2. So any pi/2 angle, there's going to be an asymptote for secant of theta. So if we take a look over here, we could see that sine of theta is equal to 0 when the y-coordinate is 0. So we can see that that's going to happen at 0 and at pi. So notice that if I plug in 0 or pi, or if we continue 2 pi, or if we go in the reverse direction, -pi. So these are all the locations along the x-axis where the sine value is equal to 0. So we can use this fact to answer a really important question as well about tangent and cotangent. So if we look at the tangent function, tangent of theta is equal to sine theta over cosine theta. And so notice that because there's a denominator of cosine theta, we should realize that there are going to also be asymptotes at the exact same places that secant of theta had asymptotes. And because we know that cotangent of theta is equal to cosine theta over sine theta, we now see that because sine theta is in the denominator, that cotangent of theta will have the exact same asymptotes as cosecant of theta. So sine and cosine have no asymptotes because there's never a time that I'm not going to get an x-coordinate or a y-coordinate, since remember that's what cosine theta and sine theta stand for. But when we now try to find each of the other 4, there's certain times where the denominator will be 0, and that's our starting point for where we're going to actually be plotting our values. So if we now take it one step further, not only could we find the asymptotes, but we could also find x-intercepts for these functions. So we should see that x-intercepts occur where the numerator is 0. So x-intercepts for tangent occur where sine theta is equal to 0. Similarly, we should be able to see that cotangent of theta will equal 0, or we'll have an x-intercept, again, when the numerator is 0. So the x-intercepts for cotangent will happen when cosine of theta is equal to 0. So we can still see that sine and cosine values that equal 0 are going to be very important components for tangent and cotangent, some of which are going to yield asymptotes, some of which are going to yield x-intercepts. So let's take a look at more points by looking at our unit circle as we rotate around. So here we have our unit circle. And keep in mind that tangent of theta is found by simply taking sine over cosine, which is our y coordinate divided by our x coordinate. So we're going to start by just coming up with a table of y values for tangent theta. And then we're going to use the fact that cotangent of theta is the reciprocal to just easily find what those values for cotangent of theta will be. So let's start with a couple of easy points here. Let's start with our quadrantal angles. So at 0 and pi. So if we take a look at 0, at the angle of 0, the tangent value is the y coordinate over the x coordinate. In other words, 0 over 1. So 0 over 1 gives me a y coordinate of 0. And likewise over at pi, I know I'm also going to get a y coordinate of 0. Which should be pretty obvious here because that would imply that the x-intercepts are 0 at 0 and pi. And we just saw right up here that x-intercepts were going to occur where the sine value is 0, which makes sense. So that's why you have your unit circle to kind of give you all of the ratios that you're going to need. If we now take a look at the other quadrantal angles at pi over 2 and at 3 pi over 2, then I can see that now the values that we get for our tangent are going to be y over x, or -1 over 0. Either one of those is going to yield an undefined value. So you can see that what we have here are just the values in the first two quadrants. That's going to be enough for us to at least start to see what the graph is going to look like, and then we can extend that to other quadrants as well. But that must imply then that at pi over 2, tangent is going to be undefined. So far, let's just go ahead and use that fact to find out our cotangent values. Obviously, if 0 is the ratio here, then the reciprocal of 0 is going to be 1 over 0, and therefore cotangent will be undefined, while pi will also give me undefined. And if we take a look at where it used to be undefined, if I were to now switch these values and take the reciprocal, cotangent of pi over 2 will now be 0. All right, so now that we've got that, we could start to find a few other nice points. I'd now like to take a look at all of the pi over 4 reference angles. If we take a look at the pi over 4s, notice that those are the values that are halfway into each quadrant, okay? And since tangent is y over x, I'm taking root 2 over 2 and dividing it by root 2 over 2. I'm dividing by itself. So notice that each time I get pi over 4, whether I take x over y or y over x, I'm going to get the same value of 1 or -1, depending on what quadrant. So that must mean that when I go to my pi over 4 angles, root 2 over 2 divided by root 2 over 2 is 1. And the reciprocal of 1 is still 1. If I now looked at 3 pi over 4 way back here, now I can see that I'm taking a negative divided by a positive. It's still going to give a ratio of 1, but now it's going to be -1 at 3 pi over 4 because the reciprocal of -1 is still -1. So now we have some really nice simple points to plot. If I were to plot my graph from 0 to pi, then I should also recognize that if 0 is an x-intercept and pi is an x-intercept, halfway between will be undefined, which is a vertical asymptote. And then halfway between 0 and pi over 2, I'm going to have a value of 1. And halfway between pi over 2 and pi, I'm going to have a value of -1. So let's start by taking a look at what these graphs already are going to look like by just at least plotting these values. So for the graph of y equals tangent x, we went ahead and plotted our vertical asymptote at pi over 2, where cosine of theta was 0. And then we had our x-intercepts on either side of that asymptote at 0 and pi. But if you notice on the cotangent graph, where the x-intercept used to be 0, now it's an asymptote. And same thing that happens at pi. Pi also has an asymptote. And where the asymptote for tangent used to be, that's now going to be an x-intercept. But notice that the pi over 4 answers are going to be the same because the reciprocal of 1 is 1 and the reciprocal of -1 is -1. So when we plugged in pi over 4 and got an answer of 1, we got the same thing over here for cotangent. And so you may already start to see what's going to happen here, and I'm going to ruin the surprise a little bit and show that obviously these points have to connect over here, right, somehow. And I also see that this is an asymptote, so it's got to come down. And I see that this is also an asymptote, so it has to come up. So that's in general what it looks like is going to have to happen. Same thing over here. It looks like I'm going to have to come up in this direction and down in this direction. And even though that's a pretty ugly graph for now, I recognize that it appears that cotangent is decreasing in between asymptotes. And more importantly, it goes on forever. There's never a boundary to how small or large my tangent values can be. And I'll give you a real brief understanding of why. Let's just say we wanted to look at tangent of theta. And we wanted to look at the angle of 89 degrees, really, really steep, okay? Well, notice that the y value would be quite close to 1, while the x value would be extremely small. So if you take a large value and divide by a really small value, then you're going to get an absolutely massive number. And so what we should recognize then is that tangent can go off to infinity, but it could also go to negative infinity for very similar reasons. If I were to go back in the negative direction and pick something just above, at this point, just above 90 degrees, maybe 91 degrees, it would be a really tall or a really large y value, but now the y value or the x value would be extremely small in the negative direction. So it goes off to negative infinity. So I'm going to fill in the rest of these values over here for the values of pi over 6 and pi over 3, just to get a couple more points to see exactly what's going on, and then we'll come up with our basic graphs. We're going to look at, first of all, root 3 over 2, 1/2. So at the angle of pi over 6, tangent of pi over 6, okay, if I'm finding tangent of pi over 6, then that's going to be my y value over my x value. But if I multiply by the reciprocal, that becomes 1 over root 3. And when I rationalize the denominator, I get root 3 over 3. So my pi over 6 value is going to give me a value of root 3 over 3, which is actually approximately 0.6. Well, that must mean as well that if we look at 5 pi over 6, which is at the exact same location, the values are going to be this, or the ratio is going to be the same. The only difference is that now it's going to be negative root 3 over 3, which we should realize is approximately negative 0.6. So if we plot those down on our graph, then that would imply that at the angle of approximately pi over 6, which you should realize is about a third of the way down here, here's pi over 6, I could see that now I'm plotting my value of approximately 0.6, a little over halfway. And if I plot 5 pi over 6, which is a little bit greater than 3 pi over 4, approximately right here, you can see that that's 5 pi over 6. That's going to give me a y value of negative 0.6, so a little more than halfway down there. Okay. So we can now see on our pi over 3 angles, our pi over 3 angles are going to give us the reciprocal of this. So if I now take a look at pi over 3, okay, which is going to be this value, Now I'm taking root 3 over 2 and dividing by 1/2. And when I multiply by the reciprocal, I simply get root 3. So at pi over 3, I get the value of root 3, while at 2 pi over 3, it must be negative root 3. So root 3 is approximately 1.7. So I'd like you to realize that that's bigger than the values or the range of sine and cosine. Sine and cosine can't exceed 1 or negative 1. But now we already see that tangent is now larger, okay, larger than 1 and smaller than negative 1. So if we now plot those down on our graph, we could see that at pi over 3, which is about 1/3 of the way over here, larger than pi over 4, that now my value is way up at 1.7. 1.7. And if I take a look at 2 pi over 3 rather, which is approximately 2/3 of the way between these values, smaller than 3 pi over 4, I could see that my y value is now going to be negative 1.7, which is about down here or so. So I should see that that's approximately negative 1.7. So this gives us a better look at as to why now, starting at the angle of 0, my tangent values continue to infinitely increase as I get closer and closer to pi over 2. But then once I get past pi over 2, my tangent values again begin to constantly increase until I get close to pi. Let's try to draw a nicer graph there. Okay. And so it appears that tangent is always increasing. And that's something that's really helpful to recognize. Tangent, no matter what, is always getting larger. When I take the values of y divided by x, it will always be increasing. There's going to be gaps, but it'll be increasing nonetheless. So I'd now like to take a look at a way to help us to memorize the values here. There's a couple of important values. These ratios for tangent show up pretty regularly. And I'd rather not have to go through this whole process of evaluating and multiplying by the reciprocal and doing all of that. So instead, let's take a look at how we can remember these values, okay? So if you remember that tangent has asymptotes at each of the pi over 2's, then any of the pi's, multiples of pi, will become 0. I'd like to focus and then halfway in between these values, pi over 4 will be 1, and this one is relatively simple to remember because that's going to be the same value divided by itself. The ones that oftentimes we have difficulty remembering are the pi over 6 and the pi over 3. So I'd like to focus on the value of pi over 6 and the value of pi over 3. Okay. Now this is a really corny way to remember, but it's always helped me to remember this. If I remember that, if I at least memorize that these two values show up, I want to make sure that they go with the right value. So how do I remember that pi over 6 goes with root 3 over 3 and pi over 3 goes with 3? And the way that I've always remembered it is in pi over 3, there's 1 3. Therefore, the answer has 1 3. Pi over 6 now must have 2 3's in order to give me the denominator of 6. It's a really cheesy way to figure it out, but it's a way that helps me remember. So pi over 6 gives me root 3 over 3, and pi over 3 gives me root 3 over, or it just gives me root 3. Now by taking the reciprocals of each of these values, I ended up filling in the rest of my y values for cotangent. And now one thing that you should recognize about cotangent is that between the asymptotes that occur at 0 and pi, look at how root 3 is the largest value, and then it decreases to 1, decreases to root 3 over 3, decreases, still decreasing into the negative, still decreasing into the negative, still decreasing further into the negative. So it appears that cotangent is always decreasing between asymptotes. And so that should make sense that if I were to plot those points as well, I should sure enough recognize that by plotting these, and I won't plot all of those values again, but plotting these should give me a graph that is decreasing from 0 to pi over 2 and continuing to decrease all the way until pi. So cotangent theta is always decreasing. So these are kind of the standard graphs of cosine theta and tangent theta, or so y equals tangent x and cotangent x. But there's a couple of things to remember about the differences between them. One thing, they have an infinite range. So they can extend all the way in the positive and negative y directions. Second thing to remember is that the asymptotes for tangent occur at all of the pi over 2 multiples, while my asymptotes for cotangent occur at all of the pi intervals. So we should see that for both of these, functions, the period, which is 1 full cycle, is not 2 pi. Remember that sine and cosine repeated the same pattern once it got from 0 to 2 pi, and then it started again from 2 pi to 4 pi. But now we should realize that for these, the period is actually just pi. By the time I move past pi, I know that I'm going to get, the exact same graph. More specifically, once I go any multiple of pi, if I were to go from pi over 2 to 3 pi over 2, the graph would start to repeat again. So I'd like to take a look at Desmos. So here you see the graph of y equals tangent of x. And let's take a couple of looks as to why this is true. This is y equals tangent of x because notice that first of all, it's increasing in between our asymptotes. I could also see that the graph has asymptotes at all of the pi over 2 angles, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on. And so notice that this pattern repeats every pi units. So from negative pi over 2 to pi over 2, that's a distance of pi. From pi over 2 to 3 pi over 2, that's another distance of pi. So what we should recognize then is that we really only need to graph one period because it's going to repeat itself every other time. Now, another thing I'd like to recognize here is that there's a point at, sure enough, at 1 at pi over 4. When I plot halfway between 0 and pi over 2, at pi over 4, I get an answer of 1. And so the standard graph that we're going to plot is not going to be what we plotted earlier, which extended from 0 to pi, but instead, because that actually only has half of this piece and half of the piece down below, we're going to plot between asymptotes. And so the standard graph for tangent x is going to be from negative pi over 2 to pi over 2, hitting the x-axis halfway in between. So from now on, when we start with our basic graph of y equals tangent x, we're going to assume that our asymptotes are going to be at negative pi over 2 and at pi over 2, and that tangent x will increase between our asymptotes. So let's take a look at how cotangent x differs. Remember that the zeros of tangent will now become asymptotes, and the asymptotes for tangent will now become zeros. Now for the graph of cotangent of x. Just as we saw when we derived each of our y values and plotted our points, we saw that cotangent is now decreasing between asymptotes. But not only that, notice how my asymptotes are now at all of the multiples of pi. So it's 0, pi, 2 pi, negative 2 pi. And so when we plot our values for cotangent of x, we don't need to plot 4 periods or even 2 periods. We're going to plot 1 period. And the standard period that we're going to plot is simply going to go from 0 to pi. When we plot the standard period, we're going to recognize that pi over 2 is going to be an x-intercept halfway between 0 and pi. But 2 other important points that we're going to plot are going to be right here at pi over 4, halfway between 0 and pi over 2. And right over here at 3 pi over 4, halfway between pi over 2 and pi, those values are going to be at 1 and at -1. So just like when we graphed sine of x, cosine of x, we had 5 values on our x-axis, that's going to be the same thing for secant and cosecant of x, and it's also going to be the same thing for tangent of x and cotangent of x. Every time we graph, we're going to plot our 5 most important values along our x-axis. So as we just saw from Desmos, the standard graph for y equals tangent x will always be increasing, and the asymptotes will be at each of our pi over 2 angles on the left side of the y-axis at negative pi over 2, and on the right side of the y-axis at pi over 2. Same thing for y equals cotangent x. Y equals cotangent x will now be decreasing, and the asymptotes will only be at the values of 0 and pi. Now, if I were to graph negative tangent x, notice that that would be decreasing, so it may appear to be similar to a cotangent function. And so since these graphs look so similar, you could actually write these graphs as tangent or cotangent depending on where the shifts are and depending on whether or not it's a positive function or a negative function. Let's take a look at a couple of examples. So seeing that this is a tangent function, I know that the typical angle is going to extend from negative pi over 2 to pi over 2. So from negative pi over 2 to pi over 2 is going to give me the standard period for tangent. So in order to find out the new period for tangent for this new function, we're simply going to recognize that this whole quantity is our theta. And so when we graph, we're going to have to figure out where are my new asymptotes going to be. So now I know that 2x minus pi over 3 is going to have to be between negative pi over 2 and pi over 2. So in a very similar way to what we did with sine and cosine in order to find out what the new period was, we're doing the same thing, only now we're finding the new asymptotes. So we're going to start by adding pi over 3 to each of these quantities. Then we need a common denominator of 6 in order to do so. All right. So if we do this, we get negative 3 pi over 6 plus 2 pi over 6 is negative pi over 6. So the left side is negative pi over 6, which is less than still 2x in the middle. And now if I do the same thing here, 3 pi over 6 plus 2 pi over 6 gives me 5 pi over 6. Now these are not my asymptotes yet because I still have to divide by 2. So if I divide each of these by 2, now I get what my new asymptotes are going to be, which are going to be negative pi over 12 and 5 pi over 12. So knowing that, we can start to graph this by just at least plotting our asymptotes. So as with any of the other trigonometric functions, we're going to be plotting our 5 special points for each period. In this case, the leftmost asymptote is going to be a negative pi over 12, and the rightmost asymptote is 5 pi over 12. And so if we draw these asymptotes, we know that the graph of tangent will be increasing in between these asymptotes. We should also remember that halfway in between the asymptotes, there's going to be an intercept, an x-intercept. So we've just got to find out where that x-intercept is by, again, finding our average. So the average between negative pi over 12 and 5 pi over 12 means I just have to add the two and divide, take their average. So 4 pi over 12 divided by 2 is 4 pi over 24, which is just pi over 6. So I know that the 0 is going to occur at pi over 6. All right, well, if we want to now find where the midpoints are, the midpoints of these are also going to be important because those are going to give some special values as well. So let's go ahead and find, first of all, what those x coordinates are first, and then we can continue from there. So now we're going to add negative pi over 12 plus pi over 6 and cut it in half. Okay, so getting a common denominator of 12, that gives me pi over 12 divided by 2, which is now just pi over 24. So now we see that this value here is pi over 24. And something special will happen there that we'll see in a minute. And same idea, we're now going to add pi over 6 plus 5 pi over 12 and cut it in half. Well, if I get a common denominator of 12, that's 5 pi over 12. 5 pi over 12 plus 2 pi over 12 is 7 pi over 12. Divided by 2 gives me 7 pi over 24. So now we have a couple of our important values here. And now we can see that the y-axis is going to be right in between my negative and positive. So I always wait to fill in my y-axis just to make sure that I'm putting them at the spot in between the negative and positive. Now that we have our y-axis, you should remember that halfway in between the 0 and the asymptote, since I know that this graph will be increasing, I know that what ended up happening here is that halfway between the asymptote and the 0, I'm going to be plotting at -1, and halfway between the 0 and the asymptote on the other side, I'll be plotting at +1, which will allow me to increase in between. But we haven't really accounted for this coefficient of 3 yet, and we want to see how that is actually going to affect the graph. Now, there's a couple of things to realize here. Anytime we multiply a function by 3, you might remember that what that does is it stretches the graph vertically. So where this value used to be pi over 24, or I'm sorry, used to be +1, it's now going to be 3 times as tall. So it's actually going to stretch up to 3. While now where this value used to be at -1, it's now going to stretch 3 times as tall. -1 times 3 is now going to stretch down to -3. So we don't plot those points at 1 all the time unless the coefficient here happens to be 1. But because we saw that it was 3, we know that that's where we're going to plot the midpoints between the zeros and the asymptotes. And now at this point, we can connect our graph. We see that this is going to get closer to the asymptotes over here. This is going to curve down and get closer to the asymptotes here. I know that the asymptotes are relatively spread out, so it kind of looks like a line right now, but keep in mind that they are increasing and that they're getting close to those asymptotes. So let's take a look at a cotangent graph. So for this cotangent function, the first thing that we might recognize here is that there's an extra constant being subtracted from the end. Keep in mind that that's automatically going to move my graph down 2 units. So we're going to have to deal with that at the beginning here to show that instead of it actually being centered around the x-axis, now it's going to be centered around y equals -2. The second thing to recognize is that in general, my theta, my angle for cotangent, is going to be between the asymptotes of 0 and pi. So since those are my standard asymptotes for cotangent, I'm now going to recognize that this is my theta. And so the first thing I'm going to do is I'm going to rewrite and get 4x plus pi over 2 and set that between 0 and pi to see what my x coordinates should be for my new asymptotes. So this is where we can now subtract pi over 2 from both sides. If I subtract pi over 2 from 0, I get negative pi over 2. If I subtract pi over 2 from pi, I get pi over 2. If I now recognize that when I've subtracted pi over 2, I'm still left with 4x in the middle, I now have to divide by 4. And that gives me that my x coordinates for my asymptotes are now going to be negative pi over 8 and pi over 8. So this is interesting because now this shows that the graph is going to be symmetric to the y-axis, or rather the asymptotes are going to be equally spaced on each side of the y-axis. So why don't we go ahead and draw our x-axis to begin. So since our asymptotes are at negative pi over 8 and at pi over 8, that means that halfway in between is going to be 0, which is our y-axis. And so now we want to be able to find our halfway points because those are going to be where we plot our additional points. Now typically our x-intercept would be at 0, at halfway in between. But this is where we got to be real careful here because notice we shifted down 2. So now that we're down 2, so here's -1 and here's -2 here. Okay, I should now realize that the new midline is down here at -2. So if you choose to, you could even just kind of draw this line temporarily to show that that's kind of like our new x-axis. And so if we now find half of pi over 8, I know that that's going to be a value of pi over 16. And on the other side, this will be a value of negative pi over 16. One more thing to recognize about cotangent is that it is decreasing in between asymptotes. So now I recognize that in general, this is going to look something like this, where it's going to cross through at -2. We just need to find those other 2 points that are going to occur at pi over 16 and at negative pi over 16. So keep in mind that the way we do that is by remembering what the coefficient is. The coefficient here is telling me what the stretch is. Now in the last problem, for tangent, I recognize that because the coefficient was 3, that means that the halfway points were going to be plotted at 3. But if it was 1, I was only going to plot it 1 unit away from the center. So that means that because the coefficient is 1 and it's decreasing in between, then there's going to be a point over here somewhere and a point over here somewhere. And so we're going to plot those at the halfway point of negative pi over 16, 1 unit above this middle line. And at pi over 16, we're going to plot it 1 unit below that middle line, which means we're going to have to go to -3 in order to be able to plot our point. And so now when we plot these, I can plot negative pi over 16 at -1, and I can plot pi over 16 at -3. So this is what allowed us to shift this graph down where it used to be at these points. Now it's shifted down 2. And so we're ready to graph, and I can graph. I like to start at the center and curve upwards towards my asymptote, and then go back to the center and curve downwards towards my asymptote. And that's the standard graph of this function. Okay, so tangent and cotangent functions are going to be infinitely increasing or decreasing from -infinity to infinity, but only between asymptotes. So if we only wanted to graph one period, we just simply need to find out what those asymptotes are by setting up a compound inequality in order to find out what x values to plot for my asymptotes.